There was a person you disliked the moment you met them. You could not have told anyone why. They had done nothing wrong, the handshake was ordinary, the smile was perfectly acceptable. And yet somewhere behind your ribs a verdict had already landed, a physical response that no amount of politeness could override. You spent the rest of the evening being civil to someone your body had already rejected. That rejection took 33 milliseconds. Your amygdala, the brain's threat classification engine, had processed their face through a subcortical pathway that bypasses conscious vision entirely and delivered its verdict before you had formed a visual image of who you were looking at. Simultaneously, your heart's electromagnetic field was interacting with theirs. Your nose was running molecular analysis on their skin chemistry, and a system built from the physics of coupled oscillation was already determining whether their nervous system was compatible with yours, or whether their presence would cost you energy for as long as they remained in the room. 5 biological systems running in parallel, all reporting before the conscious mind had a single opinion to offer. And there is a molecule on their skin that your nose may have been reading for genetic compatibility, the result determining whether their proximity felt right or fundamentally wrong. That mechanism comes later. Start with how that speed is possible, because the architecture explains everything that follows. The amygdala receives visual input through 2 pathways simultaneously. The slow pathway runs from the retina through the lateral geniculate nucleus of the thalamus to the primary visual cortex, where the image is processed in detail, edges extracted, features identified, the face assembled into a recognizable percept. This takes 100 to 200 milliseconds. The fast pathway, the subcortical route, runs from the retina through the superior colliculus and the pulvinar nucleus of the thalamus directly to the amygdala, bypassing the visual cortex entirely. This pathway delivers a low-resolution, coarse representation of the visual input in roughly 12 milliseconds. The amygdala's threat classification, using this coarse input plus additional processing, is complete in approximately 33 milliseconds. 33 milliseconds. A third of the time it takes to blink. The amygdala has classified the face before the visual cortex has finished building the image you will consciously see. Classification runs on statistical pattern matching, not against a fixed template, but against a probabilistic model built from every face the amygdala has processed across a lifetime. Tens of thousands of faces, each one encoded not as a photograph, but as a statistical distribution. The average spacing of features, the typical range of facial symmetry, the baseline patterns of muscle tension that correspond to different emotional states, faces that fall close to the statistical center of the distribution. Symmetrical, typical in proportion, carrying neutral or positive muscle tension patterns, are classified as safe with minimal amygdala activation. Faces that deviate significantly from the statistical average, in asymmetry, in proportions that fall outside the learned distribution, in muscle tension patterns associated with negative emotional states, trigger elevated amygdala activation. Probabilistic, not deterministic. The amygdala is not identifying a specific threat. It is flagging statistical anomaly, anything that deviates from the model of safe that a lifetime of face processing has built. This is where the microexpression research becomes specific. Paul Ekman, across decades of cross-cultural research, documented that certain facial expressions are universal. The same muscle activation patterns convey identical emotions across every culture studied. The expressions are produced by specific facial muscles: the corrugator supercilii for frowning, the orbicularis oculi for genuine smiling, the levator labii superioris for disgust, the frontalis for surprise. When a person is experiencing an emotion, they are attempting to conceal suppressed anger, hidden contempt, masked anxiety. The facial muscles that would express that emotion fire involuntarily for approximately 40 milliseconds before the person's conscious control suppresses them. These are microexpressions. 40 milliseconds of genuine emotion leaking through the controlled mask. 40 milliseconds is below the threshold of reliable conscious visual perception. The observer almost never detects them. The amygdala detects them. Through the fast subcortical pathway, The amygdala receives and processes the microexpression before the visual cortex has finished rendering the face the observer will consciously see. The result is a feeling: discomfort, distrust, a sense that something does not match, without any conscious awareness of what produced it. You looked at the person. They were smiling. You felt uneasy. The smile was real for the muscles the person could control, and false for the muscles they could not. Your amygdala caught the discrepancy. Your conscious mind will never know what it saw. That is the gap between what the body detected and what the mind can explain. Hundreds of encounters across a lifetime have carried this pattern. The person at a gathering whose smile felt wrong, whose friendliness produced the opposite of comfort, whose face was saying one thing, while something beneath the face was saying another. You could not have explained it. You said something was off about them. What was off was a 40-millisecond burst of concealed emotion that your amygdala classified as threat relevant and your cortex never consciously registered. You may have noticed that you were right more often than chance would predict. The colleague whose friendliness masked resentment that surfaced months later. The new acquaintance whose warmth felt performative, who turned out to be exactly as untrustworthy as your first impression suggested. The person everyone else liked, but who produced in you a persistent, low-level vigilance you could never justify to anyone who asked. In each case, the information was available. In the microexpressions the face could not fully suppress. In the postural tensions the body could not relax. In the micro-movements of facial muscles that operate outside voluntary control. The amygdala had the answer in milliseconds. The rest of you took months. But the amygdala also flagged people who turned out to be perfectly fine. The stranger whose face carried asymmetry from genetics rather than dishonesty. The colleague whose neutral expression was misread as hostility. Those misfires are less memorable than the hits, which is why the system feels more reliable than it is. Confirmation bias preserves the hits and discards the misses. The amygdala is fast and often right. It is not infallible, not mystical instinct, fast biology. Pattern recognition operating at temporal resolutions below the threshold of awareness, using a statistical model trained across a lifetime of faces. While the amygdala is processing the visual channel, your body is broadcasting and receiving electromagnetic information that neither person is aware of. Your heart generates an electromagnetic field with every beat. 60 to 100,000 cardiac muscle cells depolarise in a coordinated wave across the heart tissue, beginning at the sinoatrial node, spreading through the atria, pausing at the atrioventricular node, then cascading through the ventricles via the bundle of His and Purkinje fibers. This coordinated electrical event, what an electrocardiogram records, produces an electrical signal strong enough to be measured not only on the skin surface, but at a distance from the body. The heart's electrical output is approximately 60 times greater in amplitude than the brain's electrical activity. Maxwell's equations describe what follows. Every moving charge creates a magnetic field perpendicular to its direction of flow. The magnetic component of the cardiac field, generated by those electrical currents, extends several feet beyond the body's surface. The field strength decreases with distance according to an inverse relationship. Weaker at greater distances, but detectable with sensitive magnetometers at distances that encompass normal conversational proximity. At the distance of a handshake, the cardiac magnetic field of the person across from you is measurable. At the distance of a dinner table, it is detectable. You are sitting in each other's cardiac fields every time you share a meal. When two people are in proximity, their cardiac electromagnetic fields overlap in the space between them. The measurement of the field is established. Physics. Cardiac magnetometers detect it routinely. The degree to which the nervous system reads and responds to another person's field at conversational distances is still being quantified. The field is measured, but the social reading of the field is plausible rather than confirmed to the standard the other mechanisms have reached. The proposed pathway runs through mechanoreceptors and the afferent channels of the autonomic nervous system, the neural routes that carry information from the heart to the brain about the body's internal state through the vagus nerve and the sympathetic cardiac nerves. The information reaching the brain would not be a conscious perception of the other person's heartbeat. It would be a shift in the autonomic baseline, a subtle change in the body's internal state that registers as comfort or discomfort depending on the characteristics of the field being received. Coherence is what matters. A heart rhythm that is regular, with high heart rate variability. The beat-to-beat variation that indicates healthy parasympathetic function and autonomic flexibility generates an electromagnetic field that is ordered and rhythmically coherent. A heart rhythm that is irregular, with low variability and high sympathetic activation. The pattern of chronic stress, anxiety, or physiological threat response generates a field that is electromagnetically disordered. The receiving nervous system responds differently to each. Coherent cardiac fields in the surrounding space are associated with parasympathetic engagement in the receiver. The autonomic system settles, heart rate variability increases, the body moves toward the recovery state. Incoherent cardiac fields are associated with sympathetic activation in the receiver. The autonomic system alerts, heart rate variability decreases, the body shifts toward vigilance. Rooms carry this. A dinner party where one guest changed the atmosphere without saying anything provocative. The table tightened, the conversation became more effortful, the evening felt like it was costing energy it should not have cost. A waiting room where a stranger's presence made the space uncomfortable in a way that had nothing to do with crowding or noise. A family gathering where one person's arrival produced a collective shift in the room's autonomic baseline that everyone felt and no one mentioned. In each case, the person may have been carrying an incoherent cardiac field generated by chronic stress or acute emotional disturbance. The people in the room were detecting the field through autonomic pathways that operate below conscious awareness. The unease was real, the measurement was real, the mechanism was electromagnetic, operating through the physics of cardiac electrical activity and the biology of autonomic afferent signaling. A different channel operates simultaneously, slower than the amygdala's visual classification, but carrying information that the visual system cannot access. Your nose. Every person emits a continuous cloud of volatile organic compounds from their skin. Molecules shed from the epidermis, carried in sweat, released through sebaceous secretions. The composition of this molecular cloud is unique to each individual, as distinctive as a fingerprint, and far more information. Rich. Hundreds of distinct compounds, including aldehydes, ketones, carboxylic acids, and terpenes, are present in the headspace surrounding every human body. The relative concentrations change with emotional state. Cortisol-related metabolites increase under stress. Androstenedione fluctuates with hormonal status. Lactic acid concentration shifts with physical exertion. The cloud is a continuous broadcast of biochemical information that the person cannot suppress and usually cannot detect on themselves. Your olfactory system, 10 to 20 million receptor neurons in the nasal epithelium, each expressing one of roughly 400 different olfactory receptor types, detects and classifies these molecules with a sensitivity and specificity that approaches analytical chemistry. A single olfactory receptor can respond to concentrations in the parts per trillion range. The combinatorial coding, where each molecule activates a specific pattern across multiple receptor types, allows the system to distinguish thousands of different molecular signatures. The nose does not experience this as chemical analysis. What reaches awareness is a social impression. Comfortable, uncomfortable, attractive, repellent, that arrives before any conscious thought about the person has formed. Among all the molecular signals the nose detects, the mechanism that has received the most rigorous study involves the major histocompatibility complex, MHC, the family of cell surface proteins that the immune system uses to distinguish self from non-self. Every cell in your body displays MHC proteins on its surface, molecular identity tags that allow your immune system to recognize the cell as yours and not destroy it. Foreign cells, bacteria, transplanted tissue, virus-infected cells display different MHC proteins, and your immune system targets them for destruction. Each person's MHC profile is effectively unique, a molecular fingerprint of their immune system's recognition capabilities. MHC proteins, or their metabolic breakdown products, are present in skin secretions and sweat, shed continuously into the volatile molecular cloud that surrounds every person. Klaus Wedekind at the University of Bern tested olfactory detection of MHC directly in 1995, and the experiment was elegant in its simplicity. Women were asked to smell t-shirts worn by men for 2 consecutive nights without deodorant or fragrance, and to rate the attractiveness of each scent. The men's MHC profiles were typed genetically. The result was consistent and specific. Women rated the scent of men with dissimilar MHC profiles as most attractive, and the scent of men with similar MHC profiles as least attractive, sometimes describing similar MHC scents as actively unpleasant, as wrong in a way they could not articulate. The preference is biologically logical. Offspring of parents with dissimilar MHC profiles inherit a broader range of immune recognition capabilities, conferring greater resistance to a wider range of pathogens. The nose is performing a genetic compatibility assessment and reporting the result as a social feeling, attraction or aversion, without the conscious mind having any awareness that immune genetics are being evaluated. MHC preference extends beyond mate selection. It runs continuously in every social encounter, one signal among many, contributing to the sense that some people feel right to be near and others do not. One finding from Wedekind's work deserves specific attention. Women taking hormonal contraception showed a reversed preference, attracted to similar MHC rather than dissimilar. The synthetic hormones were altering the olfactory system's genetic screening at the molecular level, changing who smelled right and who smelled wrong. A person's deepest, most apparently instinctive reaction to another person's physical presence, the feeling that their proximity is right or fundamentally off, can be pharmacologically reversed by a pill that changes the hormonal context in which the olfactory system operates. The instinct was never mystical. It was molecular, and it was malleable. Let that settle. The most apparently hardwired social response you carry, the one that feels like it comes from somewhere deeper than thought, can be reversed by a change in hormonal chemistry. The biology is running the preference. The biology can be overridden. Someone who smells wrong to you, not obviously, not in a way you could describe, but in that indefinable quality that makes you want to increase rather than decrease the distance, may be too genetically similar to you for your immune system's preferences. The aversion is not personal. It is genetic screening, running through 400 receptor types in your nasal epithelium, reporting its result as a social emotion that feels like judgment, but is, underneath, biology, a deeper olfactory mechanism. Luca Turin's vibrational theory, proposed in 1996, suggests that receptors may detect not molecular shape, but quantum vibrational frequency, making the nose a quantum spectrometer. The theory is contested, but supporting experiments showing that fruit flies distinguish identical shaped molecules with different isotopic masses have kept it viable. Whether the mechanism is shape, vibration, or both, what is settled is that the olfactory system reads immune genetics, stress chemistry, and hormonal status from the molecular cloud surrounding every person, and reports the result before conscious evaluation begins. 3 channels described: visual, electromagnetic, olfactory. Each one fast, each one operating below awareness. Beneath all of them, a deeper system is running that determines not whether you dislike the person, but whether their physical presence is physiologically sustainable. This is the mechanism that explained the interactions I had never been able to account for. The ones where nothing was wrong, but everything felt exhausting. Nervous systems that are in proximity tend to entrain, to synchronize their rhythms, to co-regulate each other's autonomic state. The phenomenon has been measured across multiple physiological channels. Heart rate variability patterns align between people in close proximity. Breathing rhythms synchronize within minutes of shared conversation. Cortisol secretion curves begin to correlate over the course of shared time. The underlying physics is oscillator coupling, the principle that governs the synchronization of pendulum clocks mounted on the same wall, first observed by Christian Huygens in 1665. Huygens noticed that 2 pendulum clocks mounted on a shared beam would, within hours, synchronize their swings, not because of any direct mechanical connection between the clocks, but because tiny vibrations transmitted through the beam coupled the oscillators. Coupled oscillators that are close in frequency tend to lock phase. The coupling is automatic, requires no intention, and operates through whatever medium connects the oscillators. For pendulums, the wooden beam; for nervous systems, the electromagnetic, acoustic, and chemical signals that two bodies exchange when they share a room. When two nervous systems are fundamentally misaligned, when one person's baseline arousal level is dramatically different from another's, when the frequency of their autonomic oscillations falls outside the range where coupling is possible, proximity generates the opposite of synchronization. Instead of settling, the nervous systems dysregulate each other. Heart rate variability drops rather than rises. Cortisol increases rather than decreases. The autonomic state becomes more agitated, not calmer. The body registers this as a specific form of discomfort, a desire to increase distance, a sense that the interaction is costing something, a fatigue that arrives faster than the social situation would seem to warrant. Someone who leaves you drained after every interaction, who generates a specific exhaustion that is different from ordinary tiredness, that seems to persist after the encounter ends, that you have never been able to explain because they did nothing specifically wrong, may be running an autonomic pattern that is physiologically incompatible with yours. The nervous system spends metabolic resources attempting to co-regulate with a rhythm it cannot match, failing continuously, and the energetic cost of that failure registers as fatigue. Neither person is flawed. Two biological oscillators running incompatible frequencies in one room, and the physics of coupled oscillation predicts exactly this outcome when the frequency mismatch exceeds the coupling range. But when the coupling works, and it does work, in relationships that have had decades to calibrate, the physics runs in the other direction. The body settles in the presence of a nervous system it can synchronize with. Heart rate variability increases. Cortisol decreases. The feeling of ease in someone's company, the specific quality of relaxation that decades of marriage can generate, that a close friendship creates, that the presence of someone you trust produces in the body before a word is spoken, is two oscillating systems finding a shared rhythm. The comfort is physiological, the autonomic nervous system entering a state it cannot achieve alone, regulated by the presence of a compatible oscillator in the same room. This is why the loss of a long-term partner produces physiological effects that go beyond grief. The surviving partner's heart rate variability decreases, cortisol patterns destabilize, immune function declines. The co-regulatory signal has been removed. The nervous system that had been calibrated across decades to regulate itself in the presence of a specific other nervous system is now running without the input it depended on. The body is mourning a signal, not just a person. One more system. The oldest, the most visceral, the one that explains why instant dislike sometimes feels like nausea. Disgust is the oldest social emotion, older than language, shared with other primates, rooted in the neurobiology of pathogen avoidance. The neural substrate, the anterior insula and basal ganglia, is identical to the circuitry that responds to rotting food, to visible contamination, to stimuli that signal infection risk. The facial expression is identical, upper lip raised, nose wrinkled, the levator labii superioris contracting to narrow the nasal passages and reduce inhalation of potentially contaminated air. The motor response is withdrawal. The body moves away from the stimulus. The system evolved to keep you physically distant from sources of infection. It is ancient, powerful, and fast, and for most of evolutionary history, it operated exclusively on physical stimuli. Spoiled food, bodily waste, visible signs of disease. The recruitment happened in evolutionary time. The disgust circuitry that evolved for pathogen avoidance was co-opted for social judgment. A repurposing that Jonathan Haidt at NYU spent years tracking across cultures. He expected the disgust response to track physical contamination. It kept firing on moral violations instead. Betrayal, exploitation, cruelty, activating the anterior insula identically to rotting food. The face makes the same expression. The body produces the same withdrawal impulse. This is why social aversion sometimes feels physical, visceral, like a sensation in the stomach rather than a thought in the mind. Because the neural machinery generating the response is the machinery that generates nausea. The circuitry does not distinguish between a pathogen threat and a social threat. It runs one program for both. Someone who triggers something that feels like revulsion, or the dislike goes beyond intellectual disagreement into something the whole body seems to reject, is triggering a disgust response that uses pathogen avoidance hardware on a social input. The reaction may or may not be accurate. Disgust can misfire on unfamiliarity, faces, behaviors, or cultural expressions that simply fall outside the observer's learned norms, can trigger the system without any genuine threat being present. The system is fast, ancient, and blunt. It evolved for a world of physical pathogens and was repurposed for a world of social complexity. It was not designed to navigate with precision. Recognizing the machinery does not invalidate the feeling. It contextualizes it. And the context matters, because a feeling generated by repurposed pathogen avoidance circuitry deserves a different weight in social decision-making than a feeling generated by careful evaluation. All of these systems, the amygdala's 33 millisecond facial classification, the cardiac electromagnetic field detection, the olfactory immune genetic screening, the autonomic entrainment failure, the Disgust Circuit's social repurposing, converge in the first seconds of meeting someone. They run in parallel, they report simultaneously, and they deliver their combined verdict as a single, unified feeling that the conscious mind experiences as intuition. What you call intuition is measurement, fast, parallel, multi-channel biological measurement by instruments that were calibrated across millions of years of evolution and that operate at speeds the conscious mind cannot match. The measurement can be wrong. The amygdala can be biased by unfamiliarity. A lifetime in homogeneous environments builds a model that flags difference rather than danger. The MHC screening can be altered by medication. The disgust system can misfire on cultural distance rather than genuine threat. The cardiac field interpretation remains unconfirmed at the precision the other mechanisms have achieved. The person who drains you is not villainous. They are running a different rhythm. The biology is real. The information is real. The interpretation requires the part of the brain that operates at 200 milliseconds rather than 33. The slow, deliberative, cortical processing that the amygdala was never designed to wait for. But the systems are not random. They are not irrational. And they are not nothing. Every system described here was running before you walked into the room. Every one will run again the next time you meet someone new. The only thing that has changed is that now you know what the systems are doing, and that knowledge is the beginning of choosing which of their verdicts to trust.